In this ProteusDS training session, we're going to cover some fundamentals of environmental and Metocean conditions. We're going to cover the global reference frame, some terminology and clarification on direction versus heading, environmental instrumentation, setting Metocean conditions, and also a note on the discrete fluid domain used in the software. The global reference frame is located at the default mean water surface. The red axis is positive global frame X pointing towards north. Green is global frame Y axis pointing 90 degrees east, and Z axis is positive downward. A note on direction versus heading. There's different conventions from and to depending on these terms. The way that we interpret these in ProteusDS is direction means a coming from convention. So a wind direction of 180 degrees would mean the wind is blowing from the south to the north. The convention we use for heading used in ProteusDS is a to convention. So for example, the property wind heading 0 means the wind is blowing from the south to the north. Think of heading as the same sense as the wind loading vector on a structure or vehicle. When you're working in ProteusDS Simulation Toolbox, there's a number of options in the Environmental tab to set instrumentation, things like sea height probes, water velocity probes, and things like that. This is handy for getting an understanding of what the water flow is like within the simulation, depending on current profiles you've set, but it'll also pick up on the combination of wind-induced or wave-induced particle velocities on top of the current. Just know that these instrumentation values are here, and you can set multiple probes throughout the environment space. When you're working with the current profile, there's a few most commonly used profiles. Uniform. Let's open ProteusDS Simulation Toolbox so I can show you these. So current profile under the Environment tab you'll see is here. 0 profile means no current. The most commonly used is uniform. This is pretty conservative, but it's good for an initial estimate of system performance. You can see available values here. 1, if you right click, you can see available values and click on these, or you can just type in the 1 directly. And resolve follower properties will show you there's a heading you can change, and then the speed as well. Power law is another option. Number 8. This is often used in areas where there's coastal applications or also with potentially high flow environments. The other most commonly used one is custom current profile. This is a nice way of specifying data points for the current profile along the depth. It's useful for offshore and oceanographic moorings. Different wave models. Regular airy waves are just another name for sinusoidal waves. If you go down to wave type, you can change the different properties that are used, pick different wave models. Irregular waves, this uses a spectrum, will have a number of airy wave components used to reconstruct the specified spectrum. It's very common to use a John swap wave spectrum to get an irregular wave response, so we will resolve follower properties. The wave height you specify is the significant wave height, and there's the wave heading, and this wave period will indicate the peak period. A note on repeating wave surface. The number of sinusoidal components that makes up the spectrum is the wave segments number here. So if we only pick one, it's just going to have one sinusoidal wave. So just be careful that you have enough segments for your simulation length to make sure you avoid a repeating sea surface. A good rule of thumb might be something like 75 wave components. But just use your judgment and check your simulation to see what it looks like, and build up some experience with that comfort level based on what you're looking at. Wind parameters. requires both a spatial vertical profile as well as a spectrum. The spectrum allows a gusting effect, essentially, and the profile is a boundary profile, kind of similar to the power profile with ocean currents. Start with specifying your profile. Also, there's uniform available and power law as well. Once you've specified the profile, resolve follower properties, you can then specify the spectrum on top of that, and it can be constant if you want to as well. Finally, a note on the discrete fluid domain. The environment is actually discretized into finite-sized bins. Inside of each of these bins, the fluid properties are uniform. This may be in air or water, depending on where it is above the waterline. The bins hold constant values like the density and the velocity. The default values are normally fine for almost all applications. These properties are fluid domain precision and fluid domain update period. Fluid domain precision is the power of the bin size. So a fluid domain precision of 2 means a bin size of 0.01 meters. 1 centimeter is pretty small. If you're looking at very small scale systems, maybe you're comparing some tank test results and want to simulate them at the tank test scale, you may want to consider using a fluid domain precision of 3, which is 1 millimeter size. And you just change that number. Structuring the fluid domain this way with discretized bins is a big advantage for computational performance. The fluid domain update period is the rate of time at which the bins are refreshed. If there's no bin where an object is in the environment, a new bin is always created. You should have this set to something like a small factor compared to the dynamics that are happening in the environment. So for example, if you had an irregular wave spectrum with peak period of 6 seconds or maybe 10 seconds, you know, 0.1 is probably pretty good for that. It just helps reduce the amount of discretization effect that happens in the environment through time as well. All right, so to review, we went over the global reference frame, terminology, direction versus heading. It's important to understand what those means, what the difference between those are. We looked at environmental instrumentation and setting wind, wave, and currents in the software, as well as reviewing a note on the discrete fluid domain. Thanks for watching.